In this lesson, we're looking at the relationship between segments in a circle. And in the first activity that the textbook is describing, it's wanting us to either use geometry software or a compass and straight edge to make various different circles, measure various different segments, and calculate a few things with those segments and compare our results. So geometry software is wonderful for this. And so I've already made the circle. I've measured the segments. Notice which segments are being measured here. EG, GF, CG, and DG. Notice the products that I've found here. CG times DG. So that's the product of the two parts of chord CD. And then I also multiplied EG times FG. Those are the parts of chord EF being multiplied together. And as you can see right now, those two products are the same. But maybe I just happen to luck out. So maybe if I make B bigger, those products are still the same. Maybe if I make B smaller and move D so that the intersection of the two chords is in a different place, that product is still the same. And so in your notes on page 816, part D towards the top, it says look for a pattern among the measurements and calculations of the segments. From the table, it appears that DG times GC will equal EG times GF. In the discussion, it wants us to compare our results with our classmates. We didn't do this activity in class, so what you're noticing is that no matter how big or small the circle is, that product is always the same. So what conjecture can we make about the products of the segments of two chords that intersect inside a circle? The conjecture that we could make is that the product of the parts of one chord will equal the product of the two parts of the other chord. And so you see that is in explain 1 as the chord-chord product theorem. So here are all those relationships that we noticed in the first part of the video where I was using the geometry software. You might want to pause your video. Here we're using the chord product theorem. I know that this part of the chord times this part of the chord will equal this part of the chord times this part of the chord. And so they set up the equation, solved it, and then the instructions were asking for the length of each chord. So I already know that the length of CD will be 8 because that's 6 plus 2. We needed to find the value of AE so that we could find the length of chord AB, which they did here. We're going to do the same thing in part B. HG times GJ will equal KG times GI. And then I solve for X. 9 times 8 is 72, so X is 12. HG plus GJ is 9 plus 8, which is 17. KI is going to equal KG plus GI, so that's 6 plus 12. In this your turn example, we're pretty much doing the same thing. One noticeable difference, though, is notice how they didn't give us the length of ED. However, they did tell us the length of AD. So if AD is 12 and AE is 3, then that means DE has to be 9. So that's a key piece of information that you need to realize that's a little bit different than what we did in these examples. Other than that, it's the same idea. AE times DE is going to equal CE times EB. I substitute the values in, and I have 3 times 9 equal to X times 14. So 14x equals 27, and yuck, when I divide both sides by 14, x is approximately 1.9. So I already know that the length of AD is 12. The length of BC will be 1.9 plus 14, so it'll be approximately 15.9. A little bit more vocabulary. We have talked about chords. Now we have secant segments. And a secant segment is part of a secant line. Okay, so back here we had the vocabulary that a secant is a line intersecting a circle at 2 points. Remember that a couple of lessons ago we saw that a tangent line is a line that intersects a circle at exactly 1 point. So here I have a secant AE intersecting with another secant segment CE, and so we have this secant-secant product theorem. And back here I kind of broke this property down into plain English, and so I want to do that for this property as well. Okay, because it says if two secants intersect in the exterior of a circle, then the product of the length of the secant segment and its exterior segment will equal the product. Oh my goodness, all these words. So, external times whole equals external times whole is basically what this property boils down to. So we're going to prove this theorem. The two whole secant segments are AE and CE. The external secant segments are BE and DE. So we're going to draw a couple of auxiliary segments, AD and BD. And they both intercept angle EAD, and ECB, both intercept arc BD. So that means that angle EAD is congruent to angle ECB. Angle E is congruent to itself by the reflexive property. So these triangles are similar by angle-angle similarity of triangles. We haven't seen that in a while. Therefore, the corresponding parts are going to be proportional. So that means AE is to CE as DE is to BE. By the multiplication property, of equality, I'm multiplying BE times CE on both sides because that's the common denominator of the whole equation. And when I do that, I get this relationship, which is, and now we're using it. So they've set up the equation whole times external equals whole times external. They've substituted the values in, distributed, and solved for x. The instructions also asked for the length of each secant segment, so just like we did in example 1, we're adding the parts together in order to find the whole secant segment. Similarly in part B. UP times TP is going to equal SP times RP. The length of UP is x plus 7. The length of SP is 14. I distribute to get 7x plus 49 equal to 14 times 6 is 84. I subtract 49 from both sides. And then x is 5. So the length of UP is 7 plus 5, which is 12. And then, of course, the length of SP is 14. In your turn example 6, very much the same idea. PR times PQ will equal PT times PS. Remember, the whole thing times the external part will equal the whole thing times the external part. So substituting my values in, the length of PR is 10.4 times the length of PQ is 5 equals the length of PT is x plus 4 and the length of PS is 4. In my calculator, 10.4 times 5 is 52. I distribute on the right-hand side to get 4x plus 16. Subtract that 16 from both sides. 4x is 36, so x is 9. We already knew that the length of PR was 10.4. The length of PT is 9 plus 4, which is 13. Similar idea in number 7. Remember, my paraphrased version of this property is external times whole equals external times whole. So the external part of this secant segment is 6. The whole thing is 10. The external part of this secant is 5. And the whole secant segment is 5 plus x plus x. So that's 5 plus 2x. Distribute and solve. 60 equals 25 plus 10x. 10x will equal 35 when I subtract the 25 from both sides. So x is 3.5. We already knew that the length of HL was 10. Now we know that the length of NL is 3.5 plus 3.5 is 7. And now we're looking at the relationship that exists between a secant segment and a tangent segment intersecting outside of the circle. So remember how we talked about tangent lines? A tangent segment is just a part of a tangent line. So in example 4, we're using the secant tangent product theorem. Notice what they've given it to us as. Once again, I'm going to kind of paraphrase it in plain English. External secant, times whole secant equals tangent squared. In example 4, part A, we're looking at a satellite that is 6,400 miles above the Earth, and its range is given as the length SP. So we're going to set up an equation using the secant tangent product theorem. SA is the whole secant, SE is the external, and SP is the tangent. So you see those values plugged in, and then they solve for x. When you solve for x by taking the square root of both sides, you must remember from algebra that x can be positive or negative. However, in the context of this problem, distance has to be positive, so we only look at the positive value, so the value of x is 9,600 miles. Similar idea here. BD is 2 plus x, BC is 2, my tangent segment is 5, so that's why I have 5 squared there. When I distribute, I have 2x plus 4, subtract the 4 from both sides, and I have 2x equals 21, so x is 10.5. In your turn number 9, I have a kind of a busy diagram here, so we need to look carefully at the context of the problem and what actually is circular in this problem. Here's our circular pond. Notice that from the lookout station to the nest, this is a secant segment. Notice that a path that runs tangent to the pond has this tangent segment of 100. So we're going to use the secant tangent product theorem. That means I'm using external times whole equals tangent squared. The external secant is 25. The whole secant is x. My tangent is 100, which I'm squaring. So we have 25x equal to 10,000. And when I divide 10,000 by 25, x is 400. Pause your video to work through the Your Turn Below number 10. In the elaborate problem, they're asking how is solving for y different from how we solved in example 3. So in example 3, notice where the variable is. It's the internal part of the secant. Here, the y is the external part. So what does that mean? It means that my equation will be y plus 6, the whole thing, times y equal to 10 squared. So that means I'd have y squared plus 6y equals 100. Well, this is a quadratic, and you haven't seen this in a while. You should have seen this in algebra last year. So in order to solve this, I would need to get y squared plus 6y minus 100. I'd have to bring the 100 over so that I have everything on one side of the equal. Ideally, I would try to solve this equation by factoring. Remember, that means I'd be looking for two numbers that multiply together to give me 100 but subtract to give me 6. As it turns out, there aren't any. So I'm not going to do this. I'm going to use the quadratic formula that says y equals the opposite of b plus or minus square root of b squared minus 4ac all over 2 times a. You saw this in algebra last year, or you should have. So this is my a value, my b value, and my c value. So I have negative 6 plus or minus the square root of 6 squared minus 4 times 1 times negative 100. All over 2 times 1. I keep simplifying this. I get negative 6 plus or minus the square root of 36 plus 400 all over 2. Inside that radical, I have 436, and the square root of that is approximately 20.9. So I have negative 6 plus or minus 20.9 over 2. That means that there's two possible values for y here. However, if I take negative 6 minus 20.9, that's going to give me a negative number. Negative divided by 2 is another negative number. Y can't be a negative number. So I know it has to be negative 6 plus 20.9 divided by 2, which is 7.4. In number 12, it says a circle is constructed with two secant segments that intersect outside the circle. So I'd have something that looks like this. If both external secant segments are equal, is it reasonable to conclude that both secant segments are equal? So if this equals this, and I know that this x times this whole thing has to equal this x times this whole thing, then yes, it is reasonable to conclude that. So if I call this part A and this part B, here's my explanation for why. X times A plus X would have to equal X times B plus X. I could divide X from both sides and these would cancel out. That means A plus X would have to equal B plus X. I could subtract the X's from both sides, and that means